In the absence of e power x, what happens to sine of ax plus b and sine of bx plus c? Let us see them. Y is equal to sine of ax plus b and y is equal to cos of ax plus b. You may think of one more thing. Why are we discussing with these two functions only? Why are we not able to take y is equal to tan x plus b? Is to first derivative is secant square x plus b. Second derivative is 2 secant x plus b into secant x plus b into tan x plus b into a. And again third derivative, it becomes so bulky here. So that the finding nth derivative is somewhat tedious. That is why we do not take up such things. Okay, right? Y is equal to sine of ax plus b. Y is equal to cos of ax plus b. What is the first derivative of y? Cos of x plus b into a. Second derivative minus sine of. Third derivative minus cos of. Fourth derivative sine of. So that we yn is equal to a power n into sine of n pi by 2 plus ax plus b. And so many others, lecturers and students like to take this as ax plus b plus n pi by 2. Whatever it might be, both are same. This is yn. Suppose I have y is equal to sine 2x. I like to have the third derivative. y3 is equal to 2 power n into sine of third derivative, isn't it? 3 pi by 2 plus 2x. 3 pi by 2 plus means fourth quadrant, it is negative. Therefore, it is minus cos 2x. 2 power 3 into minus cos 2x. See, therefore, minus 8 cos 2x. You can verify y1 2 cos 2x, y2 minus 4 sin 2x, y3 minus 8 cos 2x, like that. Right. What happens to the case of y is equal to cos of ax plus b? Cos of ax plus b means just like the previous case, it is a power n into cos of ax plus b plus n pi by 2. Y is equal to cos of and a power n, yn is equal to a power n into cos of ax plus b plus n pi by 2. Yes. You see, sine function and cos function, the nth derivatives up to whatever extent you can, they will be repeatedly occurring. The same similar type of functions, sin x cos x, sin x cos x, sin x cos x, like that. So there is no harm in handling with the nth derivatives for those two functions. Yes, that is why we could have noted all these formulae and the formats. Next one. Well, y is equal to 13 e power 2x minus 15 e power 3x. Then d square y by dx square minus 5 dy by dx is equal to, first option, minus 6y, second option, minus 6y, third option, 14y, none. You see, y is given e power 2x 3x. You are supposed to have d square y by dx square and 5 dy by dx. You have to find dy by dx and d square y by dx square and get them substituted here. I don't say that it is impossible. I don't say that it is difficult. At the same time, there is still an easier way to get the answer. What is that? You please observe this. Y is equal to a into e power alpha x plus b into e power beta x. Suppose you have a function of this form, then d square y by dx square minus alpha plus beta into dy by dx plus alpha beta into y is equal to 0. This you may remember very simply. This can be d minus alpha into d minus beta of y is equal to 0. What I mean to say is, by capital D I mean d by dx of d square is d square of y is d square y by dx square. Actually this is d square minus alpha plus beta into d plus alpha beta of y is 0. That is d square y by dx square minus of alpha plus beta into dy by dx plus alpha beta of y is equal to 0. This you may have to remember. Yes. So with this, d square y by dx square minus alpha plus beta 5 into dy by dx plus 6y is equal to 0. So it is minus 6y. That is minus 6y. Therefore, without calculating d square y by dx square and dy by dx, you can be in a position to answer the question as minus 6y. So the answer is minus 6y. So this is to be noted and remembered. Well done. Next one. Moreover, it can be extended. Moreover, this can be extended to any number of functions like this. What I mean to say is, suppose y is equal to a into e power alpha x plus b into e power beta x plus c into e power gamma x. You see, in such a case, d minus alpha into d minus beta into d minus gamma of y is equal to 0. You can, of course, this technique, rather this result is true when and only when alpha, beta, gamma are distinct. That is, look here, this is d cube minus alpha plus beta plus gamma into d square plus alpha beta plus beta gamma plus gamma alpha into d minus alpha beta gamma of y is equal to 0. That is d cube y by dx cube minus of alpha plus beta plus gamma into d square y by dx square plus alpha beta plus beta gamma plus gamma alpha of d square y by dy by dx minus alpha beta gamma of y is equal to 0. This can be extended to as many functions as you like, provided these alpha, beta, gamma, etc. must be distinct. It's a beautiful result. As a matter of practice, let me give you one more such problem. Let us deal with one more such problem. Y is equal to 123 e power x plus 10,459 e power minus x. Then d square y by dx square is equal to, first option, 123 into 10,459 into y. Third option, y 123 plus 10,459 into y. Fourth option, none. What is the speciality in this problem? We may be stunning by looking at these numbers 123, 10,459, whatever larger integers he may give there. We just do not touch them. Alpha is 1, beta is minus 1. Alpha plus beta is 0. So there is no question of getting any dy by dx. D square y by dx square minus y is equal to 0. Hence it is y. Hence it is y. How? D plus 1 into d minus 1 of y is equal to 0. That is d square y minus y is equal to 0. That is d square y by dx square is equal to y. So the answer is y. Answer is y. Y is equal to 3 into e power 5x minus 4 into e power minus 5x. What is d square y by dx square? You observe here, alpha is 5, beta is minus 5, alpha plus beta is 0. In such a case, d square y by dx square is alpha square into y. D plus 5 into d minus 5 of y is equal to 0. You have in the rough work d plus 5 into d minus 5 of y is equal to 0. What is d plus 5 into d minus 5? D square minus 25. That is d square y by dx square minus 25y is equal to 0. Hence d square y by dx square is 25y. It is 25y. Like that. With this expression, we have so many problems in our successive differentiation. Suppose f of x is equal to 3 into e power mx plus 5 into e power minus mx. Then what is f double dash x? D plus m into d minus m of f of x is 0. D square minus m square. That is m square y. M square into f of x. M square into f of x. We have seen almost all in these examples, this alpha and beta are distinct. What happens when they coincide? Let us see. If you have y is equal to ax plus b into e power alpha x. In this case, then d minus alpha whole square of y is equal to 0. D minus alpha whole square of y is equal to 0. To threaten you, he may give problems like the 10,595 into x plus 199 into e power 2x. Then d square y by dx square is equal to, first option, 4 dy by dx plus 4y. Second option, 4 dy by dx minus 4y. Third option, 199 dy by dx. Fourth option, none. You just do not look at these two numbers. You call this a x plus b into e power alpha x. You just note alpha. What is alpha? 2. D minus 2 whole square of y is equal to 0. What is d minus 2 whole square? D square minus 4d plus 4. That is d square y by dx square minus 4 dy by dx plus 4y is equal to 0. So d square y by dx square is equal to 4 dy by dx minus 4y. So the right option is B. The right option is B. So you please remember this one also. These are beautiful, useful, important results in which problems in successive differentiation can be made and can be solved very easily. Another model, y is equal to e power 2x into x square. What is the third derivative or the fifth derivative? What is the third derivative or fifth derivative, nth derivative, like that? Here you may have to use UV formula repeatedly. It's not a single function. In such a case, there has been a beautiful formula called Lagrange's formula. What does he say? In what context, or rather in what situation we are supposed to make use of this Lagrange's formula? Look here, as and when you look at two different functions, say u and v, whose nth derivative is supposed to be found, is said like that: u v n is equal to un into v plus nc1 into un minus 1 into v1 plus nc2 into un minus 2 into v2 and so on, etc., 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 ncn into uvn. That is just like a binomial expansion. In the first step, nth derivative for the first function, and we differentiate 0 times of second function. And that is, we do not differentiate, we just keep it like y. And next, nc1, n minus 1 the derivative, v1, like that. If you proceed, at the end, nth derivative for the second function will be obtained, and u, the first function, just comes as it is. This is what we say about Lagrange's formula. Yes, this is a beautiful formula, and in explaining this formula, existence of nth order derivatives, n minus 1th order derivatives, etc., etc., for both the functions u and v are assumed of. You must be knowing, or he must be giving in the data itself, as and when nth derivatives of a product is asked in the question, it must be given. At that situation only, we are making use of this formula. Yes. Let us consider the function y is equal to e power 2x into x square as before. There must be a clear-cut idea to have the nth derivative. You choose that function whose derivatives decrease so on. X square, first derivative is 2x, next it is 2, next it is 0, there will be a full stop. So you take x square as v. Come on. y5 I require, y5, fifth derivative. Fifth derivative of e power 2x is 2 power 5 into e power 2x into x square plus 5c1 into. In this connection, the fourth derivative of e power x is 2 power 4 into e power 2x into derivative of this is 2x. Next, 5c2 into, at this juncture we require the third derivative, that's 2 cube into e power 2x, derivative of this is 2. That's all. So that it is 32 e power 2x into x square plus 5c1 is 10, 2 power 4 is 16, 16 into 2, 32, 320 x into e power 2x plus 5c2 is 10. This is 32, 2 power 4 is 16, 16 2 so 32, 32 into 5. 32 into 5 is, what is 32 into 5? 532 is a 160. 160 into x into e power 2x. 5c2 is 10 of course. 5c2 is 10. 2 cube is 8, 8 2 is 16, again it is 160 e power 2x. If you want to get e power 2x out, you can, that is the answer. And it's not impossible to get it. This is the way we have the answer for the fifth derivative. Or if you want the nth derivative, let it be. No problem at all. Let us observe one such thing. Y is equal to xc power x. I want to have yn, nth derivative. You now just change this as e power x into x. Why should you? Because we would like to keep the function whose derivatives decrease continuously in the second place. Now you think of nth derivative of e power x is e power x into x. nc1 into n minus 1, the derivative is also e power x into 1. Stop, since it is e power x into x plus n. How beautiful it is. So what is the second derivative? E power x into x plus 2. What is the third derivative? E power x into x plus 3. What is the fourth derivative? E power x into x plus 4. Like that we observe. This is the process of using this Leibniz's result. Let us observe the question given on the board. There are certain options. I am not interested in giving the options. What is it done here? The function itself is given in terms of a determinant, and this is in this determinant there are three different functions: u of x, v of x, w of x, and the other two rows are constants. What this is f of x. What is f dash x? Again, it is a determinant. In the first row, it becomes derivative of this, derivative of this, derivative of this. What is f double dash x? Again, second derivative of this, second derivative of this, second derivative of this, and the second row, third row remain the same. Like that, the nth derivative of x is also f power n of x is equal to, what is the nth derivative of x power n? N factorial. What is the nth derivative of sin x? Sine of x plus n pi by 2. What is the nth derivative of cos x? Cos of n pi by 2 plus x. Second row and third row remaining the same. This is the nth derivative of x. Well, what is the nth derivative at 0? That is x is equal to 0, you substitute. So think of, if you place x equal to 0, this becomes sin n pi by 2, which is same as this. If you take x equal to 0 here, it becomes cos of n pi by 2, which is just same as this. What is going to happen? The first row and second row are becoming equal, in a particular determinant. If two rows are equal, then its determinant is 0. Therefore, f power n of 0 is 0. The question becomes, the function becomes so bulkier. We may feel that its derivative, oh, it's a brisk process, we may not find it immediately. Like that, some people may think of it. Ordinary student can think of it, but a beautiful way of approaching is nth derivative of f of x is you just write the nth derivative of those functions which are in the first row itself, and the second row and third row remaining the same. Therefore, f power n of 0, that what I mean to say is it is not f power n of 0, it is the nth derivative. Do not forget to put the brackets. Then it is 0. You please observe this, it's a beautiful question. Let us now observe the question given on the board. There is a peculiar special function f of x such that f of x plus y is equal to f of x plus f of y for all x, y belong to R, and f is derivable at x equal to 0. Then f is derivable at all natural numbers or integers or rationals or all reals. What is the suitable option? Let us see. Let's see, f of 0 plus 0 is equal to f of 0 plus f of 0. That is, f of 0 plus 0 is 0. This is 2 into f of 0. Therefore, f of 2 into f of 0 is equal to f of 0 means you cannot cancel f of 0. That is, f of 0 is 0. 2f of 0 minus f of 0 is 0. That is, f of 0 is 0. Also, he has given that f is derivable at x equal to 0. That is, f dash to 0 is equal to limit as h tends to 0. F dash 0 is equal to limit as h tends to 0, f of h minus f of 0 by h is equal to limit as h tends to 0, f of h by h. It is, of course, f dash 0. We keep it at a side. Now, as f is derivable at x is 0, we could have a formula f dash 0 is equal to something. We have got it. Well done. F is derivable at all. That is, we may have to search for f dash x. When does f dash x exist? Look here. lim f dash x is therefore limit as h tends to 0 f of x plus h minus f of x by h. You see, f of x plus h is equal to f of x plus f of h, isn't it? This is equal to limit as h tends to 0. In the place of f of x plus h, what can you write? F of x plus f of h minus f of x by h. Limit as h tends to 0, f of h by h is nothing but f dash 0 just now we have taken, isn't it? F of h by h as h tends to 0 is f dash 0. What is the result of your observation? What could you observe here? F dash x is equal to f dash 0, isn't it? So for any x it is f dash 0 only. F dash 1 is f of 0, f dash 2 is f dash 0, f dash 5 is f dash 0. For any x, for any real number, f dash x is f dash 0. Hence f dash x is a constant function. F dash x is a constant function. Therefore, f is derivable at all real numbers. That is, what I mean to say is f dash x exists. Of course, it is a constant function. I don't mind. For every real number x, f dash x exists surely. Therefore, it is derivable at every real number. So, what is the right option? Option D is the right option. Option D is the right option. This is the question, a beautiful question in which the conceptual item is involved. Yes. Another wing of differentiation is partial derivatives or partial differentiation. Suppose there has been a function of 2 variables or 3 variables or whatever might be the number of variables. As an example, x cube plus 3x square y minus 4y cube is equal to 0. We cannot find the derivative directly, or it is needless to find. We have to find the derivative with respect to x keeping y as constant, derivative with respect to y keeping x as constant, keeping x as constant like that. See, such things are useful or can be used as and when in our the application area of application there might be a function of more than 2 variables. Then only such things occur. Okay, we are interested in the process only. See, but let me first of all find the derivative of this with respect to x only, keeping all the other things constants. X cube 3x square, y 3y, it is a constant. For x square it is 2x, 4 is a constant, y cube is a constant, 4y cube is a constant, altogether it is 0. If you name it some f of xy, then this is dou f by dou x, we say. It is a partial derivative but not the full derivative. The another way of representing it is fx, that is partial derivative with respect to x. Similarly, dou f by dou y can also be fy. What is it? 3x square derivative with respect to y. X cube constant, hence it is 0. 3x square constant into, for y it is 1. 4y cube minus 12y square. Now of special interest is the case, again this is a function of x and y. For this also you may be able to have both partial derivative with respect to x and partial derivative with respect to y also. What I mean to say is, already we have found partial derivative with respect to x. Dou by dou x of dou f by dou x, dou by dou y of dou f by dou x can be explained. What is dou by dou x of dou f by dou x? 6x plus 6y. What is dou f by dou y of dou f by dou x? 0 plus 6x. Like that. Similarly, dou by dou x of dou f by dou y. Dou by dou y of dou f by dou y. Like that you will be able to explain. But let us first know the symbolism, and then later on we shall make use of those things in our numerical problems. First of all, know the symbolism to represent those partial derivatives, and later on we use them in numerical problems. This is also written as dou square f by dou x square or fxx. This is also denoted by dou square f by dou y dou x. It is also denoted by fyx. This is dou square f by dou x dou y, this fxy. And this is dou square f by dou y square or fyy. These are the ways in which we represent these respective partial derivatives. The main concept here in the case of partial derivatives is there is a standard and beautiful formula or theorem called Euler's theorem. What is that Euler's theorem? U is equal to f of xy. Frankly speaking, Euler's theorem can be extended to a function of any number of variables. For the sake of simplicity and brevity, I am considering for two functions only for the present. If u is equal to f of xy is a homogeneous function of x and y. What do you mean by homogeneous function of x and y? Observe this. U is equal to x cube plus y cube by x square plus y square. Third degree, third degree. This part is homogeneous. Second degree, second degree. This part is homogeneous. Total, this is of first degree. In particular, f of lambda x comma lambda y is equal to lambda power n into f of xy. If you are able to write a function like this, then it is a homogeneous function of degree n, we say. Degree n, we say. Let me be very clear. What do you mean by homogeneous function? F of lambda x comma lambda y is equal to lambda power n into f of xy. If you take lambda x in the place of x, lambda y in the place of y, what do you observe? Lambda cube x cube plus lambda cube y cube by lambda square x square plus lambda square y square. If you can cancel lambda, it can be, this is f of xy. What is f of lambda x comma lambda y? Lambda cube into x cube plus y cube by lambda square into x square plus y square. Lambda x whole square is lambda square x square. Lambda y whole square is lambda square y square. You are pulling lambda square out. F of xy. So this is a homogeneous function of degree 1. And to observe practically, numerator must be of the same degree. Denominator, every expression, every term of the denominator is of the same degree. Then the fraction, rather the rational form, can be homogeneous. Of course, the basic concept to say that a particular function is homogeneous is f of lambda x comma lambda y is equal to lambda power n into f of xy. And if you are considering a function of 3 variables, then f of lambda x, lambda y, lambda z is equal to lambda power n into f of x, y, z. Then n is called degree of that one. So it is homogeneous of degree n. F of xy is supposed to be or said to be a homogeneous function of degree n if and only if f of lambda x, lambda y is equal to lambda power n of f of x. U is equal to f of xy. is a homogeneous function of nth degree in x and y, then x dou u by dou x plus y dou u by dou y is equal to nu, where n is the degree of that expression. And if you still extend to the second derivatives also, then also it can be given x square dou square u by dou x square plus 2xy dou square u by dou x dou y plus y square dou square u by dou x dou y square is equal to n into n minus 1 into u, you can say. This is rarely used, but this is frequently used. This gives you the essence of Euler's theorem. What Mr. Euler says is that, let us observe one or two simple applications of this Euler's theorem. Then x dou u by dou x plus y dou u by dou y is equal to, he is asking, you first of all calculate the degree of that expression. First of all, numerator is of third degree, denominator is of degree half. So that is the total u is a homogeneous function of degree 3 minus half, it is 2 and half. 2 and half is 5 by 2, hence the answer is 5 by 2 into u. Why do you believe that it is homogeneous? Surely, why? Because numerator is third degree, half degree like that. Therefore, it is homogeneous and it can be said 5 by 2 into u. Similarly, x square dou square u by dou x square plus y square dou square u by dou y square plus 2xy dou square u by dou x dou y. If it is asked, what is your answer? N into n minus 1 into u, that is 5 by 2 into 5 by 2 minus 1 is 3 by 2 into u, that is 5 by 2 into 3 by 2, 15 by 4 into u. You can be able to tell the answer. Well, another application. Suppose u is equal to sine inverse of x power 4 plus y power 4 by x square plus y square. You cannot say that this is directly homogeneous, because even if you substitute lambda x and lambda y in the place of x and y, you cannot get lambda out from sine inverse function. Therefore, you do one thing. Z is equal to sin u is equal to x power 4 by x power 4 plus y power 4 by x square plus y square. Now you see Z is homogeneous, isn't it? Z is homogeneous. So that we can say that x dou z by dou x plus y dou z by dou y is equal to, that is of degree 4, this is of degree 2, so it is 2z. What is dou z by dou x? Z is nothing but sin u, cos u into dou u by dou x. So it is x into cos u into dou u by dou x plus y into cos u into dou u by dou y is equal to, what is that? Sin u, 2 sin u. You divide entirely with cos u. What is going to happen? X dou u by dou x plus y dou u by dou y is equal to x dou u by dou y plus y dou u by dou y, x dou u by dou x is equal to 2 sin u by cos u, is just nothing but 2 cot. Without doing all these steps, how to get the answer? Look here. Sine inverse of the function present inside these brackets is homogeneous. So, of degree 2, write 2u. It is sine inverse function. Its inverse is sine function. Its derivative is cos function. Sin u by cos u is tan u. 2 tan u. 2 tan u. Suppose this is given cos inverse of. Its degree is 2. 2 u. Cos function, its derivative is minus sine. Cos u by minus sine u, cos u by minus sine u, minus cot u. That is the answer. Suppose if this is given, instead of cos inverse, says it's a tan inverse. What is that? The degree is 2. 2 u compulsory. Tan u by its derivative. What is tan u by secant square u? You calculate tan u by secant square u, that is cos square u, into cos square u. Tan u into cos u is sin u, isn't it? Tan u into cos u is sin u. One more cos u is there, 2 sin u cos u, that is sin 2u. Like that. That is the way of getting the answer without doing all these steps. Not only like that, as whatever you call, suppose it is log of, then this is e power u is equal to x power 4 plus y power 4 by x square plus y square. Call me this z. X dou z by dou x, etc., etc., etc. is equal to, it is 2z. 2z is nothing but 2 into e power u. By its derivative is 2, isn't it? It is logarithmic function. Its inverse is e power u. E power u derivative is e power u. E power u by e power u is 1. Since the answer is 2u. Previously it was sine inverse. Inverse of sine inverse is sin u. Sin u, its derivative is cos u. Sin u by cos u is tan u. Like that you can have. But here, inverse of logarithmic function is e power x, e power u. Its derivative is e power u. E power u by e power u is 1. So answer is 2u. Like that, we can estimate the answer without putting any steps. Let us now think of the theoretical part behind applications of derivative. Out of them, very first, let y is equal to f of x be a given function. Let a small increment, say delta x, be given to x. Then the function becomes f of x plus delta x. Then what will be the change in f? F of x plus delta x minus f of x. It is of course termed as change in y or change in f. This is the exact change in f. Let us see an example. Suppose y is equal to x plus 1 whole to the power of 4. And I take delta x is equal to 0.001. 0.001. Then what is delta y? What is delta y? This is x and x is equal to 1. X plus 0.001 plus 1 whole to the power of 4 minus of x plus 1 whole to the power of 4. To calculate this exact change might be tedious at some cases. Then we find an approximate change, that is df. An approximate change df. This df is denoted by f dash x into delta x. What is delta y? Exact change. What is df? df or dy? This is delta f. F dash x into delta x. But you see, these two are almost approximately equal. Therefore, df is approximately equal to delta f. What is df? F dash x into delta x. What is delta f? F of x plus delta x minus f of x. From that, f of x plus delta x is equal to, you send my f of x here so that it becomes f of x plus f dash x into delta x. This gives us a beautiful formula to know the approximate value of a particular function at some with a small increment. Let us be very clear and brief. Here there are two changes. One is delta f and another is df. This is the exact change, that is approximate change. What is exact change? F of x plus delta x minus f of x. What is approximate change? F dash x into delta x. These two are equal or approximately equal? Approximately equal. So that from this we can notice f of x plus delta x is approximately equal to f of x plus f dash x into delta x. That is, f of x plus delta x is approximately equal to f of x plus f dash x into delta x. Gives us a beautiful formula to find the approximate values. What I mean to say is, everybody knows that 2 power 4 is 16. If you are asked to have 2.01 whole to the power of 4, you can make use of this. Sure. How? You take x as 2 and delta x as 0.1 and f of x as x power 4. F of x is x power 4, that is 2 power 4. F dash x is 4x cube, 4 into 2 cube. Delta x is 0.01. That is 16 plus 2 cube is 8. 8 4 is 32. 32 into 0.01 is 0.32. 0.032. So the approximate value is 16.032. You can on the spot tell me the answer. No problem at all. Let us be very clear and precise by going through some other numerical example. This is the formula that must be noted. F of x plus delta x is approximately equal to f of x plus f dash x into delta x. What is the approximate value of 2.1 whole power 4? This looks like x power 4. In name, f of x is equal to x power 4. If it is 2, we know its value pretty well, right? X is equal to 2. It is what more than this x? 0.1 more than. So delta x is 0.1. What is asked here? 2.01 whole power 4 is nothing but f of x plus delta x, isn't it? Is approximately equal to f of x, x power 4, f dash x, 4x cube, delta x, delta x. What is x power 4? 2 power 4, 16. What is x cube? 2 cube. Delta x, 0.01. 0.01, so it is 16 plus 2 cube is plus 8 4 is 32, 32 by 100 is 0.32. So the answer is 16.32. To give you the clear-cut explanation only, I have made all these steps. As we could explain in the very beginning, we can have the answer directly. How? Now you observe. This looks like x power 4. F dash x, 4x cube. If it is 2, we know that. So in the place of x, we replace 2. It is 0.1, 0.01 more than that. So delta x is 0.1 into delta x. 2 power 4 is 16. 2 cube is 8. 8 4 is 32. 32 into 0.01 is nothing but 16.32. Like that. You will be able to have the answer. Let me now calculate one more such thing. What is square root of 4.01? How does it look? Root x, root 4, 2 plus f of x is root x in our mind. What is its derivative? 1 by 2 root x. 1 by 2 root x into delta x. What is delta x? 0.01. So it is 2 plus root 4 is 2. 2 2s are 4. So 1 by 4 is 0.25. 0.25 into 0.01. It is 2.0025. It is 2.0025. It's not impossible to get the answer on this part. It is a beautiful application of the derivatives, isn't it? Next one. One more application of the derivative is monotonicity of functions. What do you mean by monotonicity? What do you mean by monotone? Mono means same. Tone means character. Same character. That the word which is meant in that way has been named of a function. What is meant by that? Look here. You observe the graphs on the board. I have drawn 5 graphs on the board. Please follow them. The function is, the graph is going up continuously. We say that it is increasing. What is meant by increasing and what is increasing? Height is increasing. For a point here, height is this much. For a point, this much. For a point, this much. Height is increasing. What do you mean by height there? Y coordinate. What is y coordinate? F of x. That is why we say that f is increasing. F is increasing. Here, going up. Naught has come down, kept stationary up to certain level. Again he is raised. Kept constant at some particular position. Again going up like that. This is increasing, but this is non-decreasing. Just like that. You observe this. The graph is falling down. So decreasing. Which is decreasing? The height is decreasing. If you take a point here, height is this much. If you take a point here, the height is this much, isn't it? If you take a point here, height is this. Here, this. Here, this. Height is decreasing. Height is nothing but y coordinate. Y coordinate is nothing but f of x. F of x is decreasing. So, by simply looking at the graph, if you want to say it is either increasing or decreasing, if the graph goes up, it is increasing. If the graph comes down, it is decreasing. Okay, what is it about this? Decreases. Stationary. Decreases. Stationary. Decreases. Stationary, but never increases. Therefore, it is not increasing. This is not decreasing. This is strictly increasing. This is strictly decreasing. But this graph, you observe, increasing, going up, coming down, going up, coming down. It is not exhibiting a stationary character, similar type of character. Mono character is not exhibiting, therefore it is not monotonic. This is not monotonic. This is monotonic in the sense say, exhibiting the same character. Increasing means increasing, it can never decrease. Increasing means increasing, it can never decrease. Decreasing means decreasing, same character, decreasing character, same character, decreasing character. It suddenly it can never change its direction. It cannot increase. This is the explanation of the word monotone property. And creating one word, monotonicity. Monotone means same character. Same character, increasing character. This is the pictorial explanation, of course. But how to define this? From this, how to give the definition for this nature, this character? x1 less than x2, if you observe, automatically f of x1 less than f of x2. It does mean if you take x1 and x2 here, this is f of x1, this is f of x2. x1 is less than x2. Automatically f of x1 is less than f of x2. And it is true for any pair of points you consider. x1 less than x2 implies f of x1 less than f of x2. Of course, x1 and x2 are the points in the domain, it must be. Well, how to explain this one? This is strictly increasing. Here, x1 less than x2. Suppose I take x1 here, x2 here. F of x1 is less than x2. Suppose I take x1 here, x2 here. Then f of x1 is equal to f of x2. So, x1 less than x2 implies f of x1 either less than f of x2 or at most is equal to f of x2 but can never be greater than f of x2. So, with that concept, we say that it is non-decreasing. No question of decreasing character. It at most increases or may be stationary at one particular region. That is why it call it non-decreasing. Well, let us come here. x1 here and x2 here. What do you observe? x1 is less than x2, no doubt. On x-axis x1 is less than x2. But you see, f of x1 is greater than f of x2, isn't it? Is f of x1 is greater than f of x2. It is monotonic, surely. Why monotonic? Exhibiting the same character. This is also monotonic, sure, exhibiting the same character. What type of character? Increasing character. That is why it is called monotonically increasing function. This is monotonically decreasing function. Decreasing means what is being decreased here? Height is being decreased. What is meant by height? Y coordinate. What is y coordinate? F of x. That is why f is decreasing here. Monotonically decreasing, monotonically increasing. Is it necessary to put the word monotonically? Theoretically it is necessary. And in the practical considerations, now and then we omit to use it. Whatever it might be, either increasing or decreasing, as and when it exhibits the similar character throughout the domain or throughout a particular region, it is monotonic, of course. Monotonic. As what do you say about this? This is, come on, if you take x1 here, x2 here, then f of x1 is greater than f of x2. If you take x1 here and x2 here, then they are equal, isn't it? So, here x1 less than x2 implies f of x1 is greater than or equal to f of x2. So, in this case, we say that it is monotonically monotonically increasing or decreasing? Non-increasing. Why are you not able to say that it is perfectly decreasing? Somewhere else it is becoming stationary. Somewhere else some f of x1 is equal to f of x2 might happen. That is why it is non-increasing. This is non-decreasing. This is strictly increasing. This is strictly decreasing. All these four things together can be called monotonic. They are monotonic. What do you mean by monotonic? Same character, either increasing or decreasing, like that. To be more precise, these are perfectly, strictly monotonic. That is why we are saying strictly increasing and strictly decreasing. And what about the last graph? It is not monotonic at all. It is not monotonic. You cannot speak of either increasing nature or decreasing nature or non-increasing nature or non-decreasing nature for the graph. So, to discuss with either increasing character or decreasing character, one must possess the graph of the function like this. We could have now seen the graphical explanation and the theoretical definition. Okay. What is the practical part in it? If a particular function is given, when do you say that it is, when do you identify that the function is increasing or decreasing? That is the task for the present.